In this part of the lecture, we will go through a constant coefficient differential equation given to us. We will try to solve it using the knowledge that we have gathered so far. As you can see, in this equation, we have both the input and output part given to us, and some initial conditions are given, and some input is given. That means we are asked to calculate the total response. If you remember, the total response or the YT, that eventual YT will have two uh, parts. One is the homogeneous solution, and another one is the particular solution. Okay. So we need to calculate both the solutions and then plug them together, and even then after that we will have the total response. From that total response, using these initial conditions, we will eventually find the actual response of this system. Okay. So following the steps that we have learned so far, how to solve these differential equations, let us begin. So at the very beginning, we can see the equation is given, and we will start with the homogeneous solution part. So to calculate the homogeneous solution, we have to assume one solution. The format of the assumed solution is that C e to the power lambda t. Okay. So for homogeneous solution, we have assumed that the solution will be C e to the power lambda t. So first different derivative of the homogeneous solution will be C lambda e to the power lambda t, and double derivative of the given or assumed solution will be C lambda square e to the power lambda t. Okay. Now if we plug these values in this case, and obviously while calculating the homogeneous solution, we have to consider that the differential equation is only available for zero input, or we will have to consider the differential equation in this format. Now here we have to plug these values. And if we plug it, we get something like this: C lambda square e to the power lambda t plus 6C lambda e to the power lambda t plus 5C e to the power lambda t equals to 0. By if we take common C e to the power lambda t, in the bracket we get lambda square plus 6 lambda plus 5, which is equals to 0. Since this is a non-zero part or non-zero quantity, so we can equate this into a characteristic polynomial that will be lambda square plus 6 lambda plus 5 equals to 0. So now we have to solve this polynomial. So this polynomial can be solved in this way. If we take lambda common here, there we will have lambda plus 5, and if we take 1 common here, we will have lambda plus 5. So eventually we get lambda plus 5 into lambda plus 1 equals to 0, which gives us the value of lambda to be -1 and -5. So as the values of lambda are distinct values, we have got, so for distinct rules, for distinct roots for of this polynomial, the homogeneous solution can be thought of in this way: C1 e to the power lambda 1t, which is e to the power minus t, plus C2 e to the power minus 5t. So this will be our homogeneous solution for the given equation. Now we have to think of the particular solution. In our previous part, we haven't seen how to go about in solving particular solution. In this video, we will look at it. what we said previously, that if any input is given for particular solution, we have to assume that for particular solution will be k into xt. So for this particular case, our assumed particular solution will be k e to the power minus 2t. Here ut is multiplied, that means this function is available at t is greater than 0. So that is the significance of the ut multiplied here. So for particular solution, this is the assumed solution. So from here we will start our process of calculating the particular solution, and already we have calculated the homogeneous solution, and then after plugging them together, that will give us the total response of this system. Okay. So for particular solution, we have assumed that the solution will be k e to the power minus 2t. So the first derivative of this solution will be minus 2k e to the power minus 2t, and taking double derivative of the assumed solution will give us 4k e to the power minus 2t. So now if we plug this value into this solution, into this differential equation, that will return this. The double derivative will get replaced by 4k e to the power minus 2t. The single derivative will get replaced by minus 2 e to the power minus 2t, and that will get multiplied by 6. So here we will get minus 12k e to the power minus 2t, and replacing this plus 5/2 will give us plus 5k e to the power minus 2t. And at the right side, we have the first derivative of xt and 4 into xt. The given value of x is e to the power minus 2t. So first derivative of xt is minus 2 e to the power minus 2t. So the right hand side of the equation can be replaced in this way: minus 2 e to the power minus 2t plus 4 e to the power minus 2t. So if we calculate further here, in the left hand side we will have the 4 minus 12 plus 5, which is minus 3k e to the power minus 2t, and at the right hand side we get 2 e to the power minus 2t. So if we equate everything, and the final value we get here, the value of k is minus 2/3. So with this discovery, we can say that the particular solution of this differential equation is minus 2/3 e to the power minus e to the power minus 2t. And obviously this is available for t greater than 0, which we can represent by plugging ut as multiplied with the whole thing. So this is our particular solution, and we have with us the homogeneous solution. The homogeneous solution was c1 e to the power minus t plus c2 e to the power minus 5t, and the particular solution we have with us minus 2/3 e to the power minus 2t. So the total response here for this differential equation is the homogeneous solution plus the particular solution. So they both together give us C1 e to the power minus t plus C2 e to the power minus 5t minus 2 by 3 e to the power minus 2t. So in this whole setup, the missing values are of C1 and C2. So using the initial conditions given, we have to calculate the value of C1 and C2, and that will give us a complete version of the total response of this system that is defined by the given differential equation. Now the job at our hand is to find the value of C1 and C2 using the initial conditions given in our questions. If we look at the initial conditions, one is given that y0, when this is the y at t equals to 0, the whole outcome will be equals to 1, and using this we will get one equation. And another initial condition is given that first derivative of first derivative of y at t equals to 0 returns minus 2. So we have to take for first derivative of this equation and check what happens for the case t equals to 0, and we have to equate it with minus 2, and that will also give us another equation. By solving the two equations, we will have to come to a conclusion about C1 and C2. Okay, now let's begin the process. So this is yt. Let us set the value of t to 0. So see what happens. So for t equals to 0, this value will become 0. This will also become 0. So e to the power 0 will give us 1. The same will happen here. So at when y 0, we get C1 plus C2 minus 2 by 3. And according to our initial condition, it is equals to 1. So if we further calculate, it returns C1 plus C2 equals to 1 plus 2 by 3, which is 5 by 3. Again, we have to take derivative of the given yt and check for the value of the derivative of yt for t equals to 0. So let us take the first derivative of this equation. That will return minus C1 e to the power minus t minus 5C2 e to the power minus 5t plus 4 by 3 e to the power minus 2t. And according to the initial condition, if we take t equals to 0 for this equation, that we will return minus 2. So if taking at t equals to 0, this will become 0, this t will become 0, and this t will also become 0. So eventually we will get minus C1 minus 5C2 plus 4 by 3, and according to the initial condition, that will return uh, minus 2. So if we further solve this, it turns out minus C1 minus 5C2 minus 2 minus 4 by 3, which is 3 minus 6 minus 4, which is 10 by 3. And at the left hand side, we have minus C1 minus 5C2, and at the right hand side, we have minus 10 by 3. So if we multiply minus 1 in both the side, we get C1 plus 5C2 equals to 10 by 3. So which we can label as equation 2. We have these two equations at our hand, like we have just calculated. So by solving these two equations, we can clearly see that we will eventually get some values of C1 and C2. And if we plug these values in our main equation, that will give us the total exact response of this differential equation. So let us move further. If we take 1 minus 2, that will give us minus 4C2 at the left hand side, and at the right hand side we will get minus 5 by 3. So the value of C2 is we are getting 5 by 12. If we plug this value into any of the equation, let us plug it into uh, equation 1, that will give us C1 plus 5 by 12 equals to 5 by 3. So C1 will be 5 by 3 minus 5 by 12, which is, we take 12 and then we get 20 minus 5, which is 15 by 12, or we can further calculate it to be 5 by 4. So we have found the values of C1 and C2, which are uh, C1 is 5 by 4 and C2 is 5 by 12. So if we plug these two values into our actual equation, that will finally give us the total response of the system that is given to us in the form of a differential equation. The final equation was C1 e to the power minus t plus C2 e to the power minus 5t minus 2 by 3 e to the power minus 2t. Let me see if I have written it correctly or not. Yes, that was the case. And here we have calculated the value of C1 to be 5 by 4 and C2 have been calculated to be 5 by 12. So if we plug these values into this equation, so that is our final answer, or the total response of the system is 5 by 4 e to the power minus t plus 5 by 12 e to the power minus 5t minus 2 by 3 e to the power minus 2t. So that is the total solution of this equation.